Hi, everybody on Galspec 2021 YouTube. My name is Brian Lemaux. I'm a researcher at the University of California, Davis, and I'm going to be talking to you today about the legacy of VIMOS in exploring and defining high-density environments at high redshift. This is work I've done in collaboration with Olga Cucciati at Bologna, my former advisor, Lori Lubin at UC Davis, Olivier Lefebvre before he passed away last year, and the VUDS and ORELS collaborations. So as you probably already heard from Bianca's talk and from Olga's talk, there's lots of reasons to study high density environments, groups, clusters, and proto-clusters at higher redshift, which are their higher redshift progenitors. And so I'll just briefly review, I'm sure Bianca already did this and Olga as well, but I'll briefly review some of the well-established trends, galaxy evolutionary trends at redshift 1 and redshift 0. A couple of the more well-known scaling relations are the star formation rate density relation, and this is generally seen as a suppression of star formation activity in high density environments to about redshift 1.5. And this is seen in the ORELS survey, which I'm a part of. This is a paper in 2019 by Adam Tomczak showing that at higher density environments, the overall star formation is suppressed on average relative to rarer galaxies in rarer environments. This is also seen in the Go Green surveys. This is a paper by Lindsay Old in 2020. Another scaling relation that's seen up to about redshift 1.5 is the color density relation. And here the relationship is between the fraction of quiescent galaxies or star-forming galaxies, conversely, as a function of environment, where in higher density environments, it's seen all the way up to at least redshift 1.5 that quiescent galaxies outnumber star-forming galaxies in high density environments, and that the quiescent fraction in the high density environments always exceeds that of the field. So why go to higher redshift? Well, there's plenty of very good reasons. The mere fact that there's very massive galaxies in high density environments, more so than in lower density environments at lower redshift, tells you that the peak of the star formation rate for these galaxies should be shifted to higher redshift, and there might be a lot of star formation activity. This kind of logic is also borne out in simulations. So this is from a paper by Chang in 2018 showing the predicted star formation rate density in extended protocluster environments. So not the cores, but really the large-scale structure surrounding the protocluster, which contains quite a bit of the redshift 0 members. And so if you look at this plot, you can pause the video if you want, but if you look at this plot at, for example, at redshift 3, about 30% of the cosmic star formation rate density is contained within protocluster environments, and such environments constitute less than 5% of the volume. So the protocluster galaxies should be far outpacing coeval field galaxies at these redshifts on average. And there's a variety of other reasons why one might want to study such environments at these redshifts, which I don't have time to go into now, but I'll talk a little bit about later in this talk. So in order to study these things, one has to find them first, and this is a non-trivial activity. There's lots of different methodologies. There's tracer populations that are very exotic, such as submillimeter galaxies or quasars. I'm going to just be talking about the galaxy trace methods. I'm sure Olga's gone over quite a few of the other methodologies. I'm not going to be talking about IGM tomography, but really just galaxy density searches. So the typical way to do this is to get a bunch of deep wide field imaging to estimate some photometric redshifts or do some color cuts, and then go after overdensity candidates with deep spectroscopy or narrowband imaging. And the standard way of doing this is, because it's observationally pretty cheap, to look for Lyman alpha emitters. So this is a subclass of star-forming galaxies which is subdominant at any redshift, but especially at redshifts 2 to 3, where it's only about 10% of the population. And so while this works, there are significant biases associated with this. So how do you get around this? Well, you get a really awesome instrument like VIMOS, and you basically just stare at the sky for a very long time, although it has to be the right sky, not the Marseille sky. but this guy at VLT. And so the idea behind the VIMOS Ultra Deep survey was to target 10,000 objects with photometric redshifts between 2 and 6, and to stare very deeply, so 14 hours per grism per pointing. And the idea behind this was to get down to the continuum for essentially all objects that we targeted, which is IBAN less than 25. So fairly faint, around 0.3 to 3 L-star at these redshifts. But you can see in this two-dimensional mosaic here, and also in the redshift histogram here, that this strategy worked, and that we were able to integrate down to the continuum to detect galaxies, all star-forming galaxies, regardless of whether or not they were emitting in Lyman alpha. So once one has a bunch of redshifts, one needs to create an environmental metric if one wants to study environment. It's a good thing to do. And so how do you do this? Well, there's a variety of different methodologies. I'm sure Olga covered many of them. But the one that we use is something called Voronoi-Monte Carlo mapping, which is basically, very, very briefly, a statistical combination of spectroscopic redshifts and photometric redshifts to create a density map like you see here. And so this is for a proto-cluster at redshift 3.3. And if you pause this, I have a little bit more information on the slide about what this method does. And so we've used this method to good effect to discover proto-clusters and proto-groups at high redshift. This one here is our highest redshift structure at redshift 4.57, detected with primarily VUDs, although we combined other surveys from VIMOS. And this is a coma-like progenitor proto-cluster at redshift 4.57 that initially had 9 spectroscopic members. And initially we saw an excess of more massive and older galaxies within the structure relative to the field. Unfortunately, now that VIMOS is retired and there's no real good equivalent on VLT for now, we've moved to Keck, and we've used DEIMOS and MOSFIRE to target this protocluster along with a couple others. And just shown down here is our current observations with Keck DEIMOS, where we have roughly quadrupled the member population at this point. And I think the total member population is something like 60, although we've just finished the observations. One of the interesting objects that was targeted as a part of our DEIMOS campaign is this object here, which is a triple merging system that was also detected with the Alpine survey using ALMA, targeting the C2 158 micron line. And why this particular object is interesting, other than it's a triple merging system, is that you can see the scales here, so very large scales. There's a very large envelope of diffuse gas here, which is about the mass of the in situ gas for these galaxies. And so this is an indication that the nascent ICM is being fed by stripping due to merging activity. Another system that we've been looking at closely with Keck is this system here, redshift 3.3. My former student Liu Shen did a paper on this in 2021, looking at 2 different BCGs, one in the main structure here and one in the substructure here. And these 2 BCGs have very different properties, as do the host structures. And Liu did a very nice job of relating the two structures to their BCGs and trying to find a coherent way that these types of systems might be formed. And the BCG that we discovered with the MOSFIRE data, I think, is 10 to the 11.6 in terms of its stellar mass. So it's really a canonical BCG that's already quiescent in this substructure formed ex situ out of the main structure of this protocluster. The final structure that I'll talk about is the Hyperion proto-supercluster. This is an immense structure at redshift 2.5. I'm sure Olga already went over it, but the total mass is about 5 times 10 to the 15. There's 7 different peaks that you can see in this rotating 3-dimensional overdensity map. And initially, from a variety of different tracer methods, different peaks were picked up, but really with the power of VIMOS, the Z-Cosmos survey, plus the VUD survey, plus a variety of other surveys, we were able to contextualize and find this whole entire coherent structure. This is also a part of the ongoing Keck Mossfire campaign. And as of now, we've more than doubled the spectroscopic member population, and we're beginning galaxy evolution studies. So finally, I want to talk about combining all these data. So those were case studies that I showed earlier. We're trying to look at scaling relations. The first scaling relation that's fairly obvious to look at is the star formation rate density relation. This is combining VUDS and Z-Cosmos, VBDS, and our own VIMOS follow-up, combined with a few other surveys. And this is looking across the 3 VUDS fields. And what we see is running from a lower density environment all the way to the peaks of the proto-clusters, a coherent and statistically significant increase in the amount of star formation activity from the low density to high density environments. This is a reversal of the Redshift 0 to Redshift 1 trend. Stellar mass effects are important. So with higher stellar mass, typically comes higher star formation rate for star forming galaxies. And so one has to normalize this out. And we spent quite a bit of time looking at how to do this. And we find even after normalizing out stellar mass effects and redshift effects, there's a statistically significant increase in the star formation rate on average running from low density to high density environments. We also see this trend change as a function of redshift. So in the lower redshift half of our sample, at about redshift 2.5, we actually see that galaxies in the lower density environments relative to the highest density environments are statistically indistinguishable in terms of their star formation rate properties. But this is not true at the higher redshift half of our sample, where we see a coherent increase running from the lowest density to highest density environments. So finally, we're trying to put this all together using the ORL survey at redshift 1, SDSS at redshift 0, and the VUDS data, along with our own Keck data, redshifts 2 to 5, and to chart out the construction of clusters using semi-empirical models and n-body simulations all the way from redshift 5 to redshift 0. And so if you're interested in how we are planning on doing this and detecting the structures, my student Denise Hung wrote a paper in 2020 showing how we can use these maps to detect structures, and did a wonderful job of looking at the purity and completeness of structures as a function of their overall mass, their spectroscopic fraction, and their redshift. So I'll put up my conclusions, and which you can pause, of course, and look at. Please do ask me any questions over the Slack channel. And since this is a VIMOS conference, I just wanted to leave with a kind of eulogy for my former mentor that came as a joint statement from his former ERC team in Marseille. So thank you very much.